Hello everyone, I am Vrishali. My topic is digital camera technology and its role in computer vision. This presentation will delve into the intersection of digital cameras, technology and computer vision, exploring key concepts, advancements and applications. In this presentation, I'll take you through the journey of how images are formed in digital cameras, the technologies that power them, and their applications in real-world scenarios like autonomous vehicles, medical imaging, and more. Let's get started. Image formation in digital cameras. First, let's understand how images are formed in digital cameras. The process starts with light capture. When light enters the camera through the lens, it focuses onto an image sensor. This sensor is the heart of the camera, converting the incoming light into electrical signals. Imagine it as a digital eye, collecting light and interpreting it into data. The lens plays a critical role here. It controls how much light enters and focuses it correctly onto the sensor. High quality lenses ensure sharp and accurate images, which is crucial for tasks like object recognition or depth estimation in computer vision. Next is sensor response. Sensors are made up of millions of tiny elements called pixels. Each pixel records the intensity of the light it receives. This raw data undergoes processing to create a coherent digital image. For example, the camera might enhance brightness, adjust color tones, or compress the image for storage. This entire process lays the groundwork for the advanced image techniques we'll discuss later. Here is an illustration that explains the working of digital camera in a simple step-by-step manner. It visualizes how light passes through the lens. It focuses on the image sensor, converted into electrical signal and then processed into a digital image. This can be a great aid in explaining the concept visually. Let's move to next. Color models in digital imaging. Now let's move on to how colors are represented in digital cameras. Digital imaging relies on color models, which provide a systematic way to describe and reproduce colors. The most common model is RGB, which uses red, green and blue as primary colors. By combining different intensities of these colors, millions of shades can be created. Think about your TV or smartphone screen. Every pixel on these devices emits red, green and blue light to form the vibrant images we see. Another model is HSI, which stands for hue, saturation and intensity. This model mimics how humans perceive color, making it easier to use in applications like image editing or computer vision tasks where human interpretation is critical. For instance, in traffic sign detection, HSI can help distinguish the colors of signs even under varying lighting conditions. There are also specialized models like CMYK used in printing and YUV common in video compression. These models demonstrate the versatility of color representation in digital imaging. Next, advancements in camera sensors. Digital cameras have seen remarkable advancements in their sensors. Two main types of sensors dominate the market are CMOS and CCD. CMOS sensors are energy efficient and support faster read speed, which is why they are found in smartphones and high-speed cameras. For example, in real-time applications like surveillance, CMOS sensors capture fast-moving objects without motion blur. CCD sensors, on the other hand, are known for their superior image quality and sensitivity to light. These are often used in professional grade cameras or scientific imaging equipments. One revolutionary advancement is high dynamic range imaging HDR. HDR allows cameras to capture details in scenes with extreme lighting contrasts. For instance, in photography, HDR ensures that both the bright sky and the dark shadows of a building are well exposed. In computer vision, HDR helps systems analyze complex environments such as identifying objects in bright sunlight and dim interiors. You can see here there are three stages: capture, tone mapping and merge. Next is camera calibration technique. Accurate imaging is only possible with proper calibration, which adjusts the camera to remove distortions and align images correctly. Let's look at three key techniques. First one is lens distortion correction. This occurs when straight lines appear curved in photos like in fish eye or wide angle lenses. Correcting this ensures that the object retain their true shapes. For instance, in 3D modeling, accurate geometry is crucial for creating realistic virtual environments. Perspective adjustment. Cameras often capture images with skewed perspectives, especially when objects are viewed from an angle. Correcting this distortion makes objects appear proportional. This is critical in applications like aerial mapping or architectural photography. Third is image alignment. In stereo vision, multiple images need to be aligned for depth perception. Misaligned images can cause errors in calculating distances, impacting applications like autonomous vehicle navigation or robotic grasping. Let's move to the next slide. This is stereo vision and depth perception. Here there are two types: triangulation and structured light. Now let's discuss stereo vision, a technique that allows cameras to perceive depth. Stereo vision mimics human binocular vision by using two cameras to capture slightly different images of the same scene. One method is triangulation, which calculates depth by comparing the position of an object in the two images. This technique is widely used in robotic navigation. Another method is structured light, where a light pattern is projected onto the scene. The deformation of the pattern helps calculate the depth. This is commonly seen in facial recognition systems like the ones used in smartphones for unlocking the device. Depth perception plays a critical role in many fields, from creating 3D maps for virtual reality to aiding drones in obstacle avoidance. Applications in computer vision. Finally, let's look at some real world applications where digital cameras and computer vision have made a significant impact. Object recognition. This technology identifies and classifies objects in an image. Applications range from image search engines to security systems that use facial recognition. Autonomous vehicles. Self driving cars rely heavily on computer vision for tasks like lane detection, traffic sign recognition, and obstacle avoidance. Cameras act as their eyes, enabling them to navigate complex environments. Medical imaging. Techniques like MRI, CT scans, and X rays used advanced imaging to visualize internal body structure. Computer vision algorithms analyze these images to detect abnormalities such as tumors or fractures, making diagnosis faster and more accurate. These examples highlight how digital camera technology power transformative applications, improving lives and enhancing industries. Here you can see this picture. It is another illustration showcasing key application of computer vision using digital cameras. It highlights areas like object recognition, autonomous vehicles, medical imaging, and robotics, making it easier to explain their real world impact visually. Let's move to the next page. So, I would like to thank you. The conclusion is digital camera technology is a cornerstone of modern computer vision. From capturing light to enabling advanced applications like autonomous vehicles and medical diagnostics, cameras have come a long way. Their continuous evolution, driven by innovation in sensors, calibration techniques, and imaging methods, promises even more exciting possibilities in the future. Thank you for your time and attention.